So this may seem really simple to you, but as an astronomer, who really, I spend most of my time going off to telescopes and looking at stuff in the sky as opposed to trying to invert skies. This has been an interesting and complicated thing for me to try to work through. I hope that some of you look at it and say, oh, I actually know how to do that better than you dumb astronomers, and then you come tell me how to do it better, because that's kind of why I'm here, hoping to see what goes on. So in astronomy, in the history of astronomy, I think has one of the first classic inversion problems that was successful in the history of science. Maybe not the first. We were debating last night what was the very first inversion problem. I will at least argue that this is one of the best known early ones, and it came out from the discovery of Uranus in the right before the turn of the 18th. Never do those numbers right, 19th century, and then tracking the location of Uranus across the sky. And this is Alexis Bouvard wrote this paper in 1820. He was the director of the observatory in Paris, and it's this fine paper with tables of Jupiter, Saturn, and Uranus and where they are in the sky, and his math for where they should be in the sky. So here's his theory on where Uranus should be with its perturbations by the gravitational poles of Jupiter and Saturn. And he realizes, you don't have to actually see what these numbers are, but he realizes that Uranus is not actually in exactly the right spot. There are errors in its position. So you can see errors here, this table, there's pluses, there's minuses, there's pluses, there's minuses. These are years. The fun thing that Bouvard did, of course, Neptune wasn't discovered until here, and he went back in time and found previous observations of Uranus, which let him really understand the orbit of Uranus extremely well. It was actually, he was trying to go back in time to find out if Uranus was on a circular orbit, therefore what they would consider a planet at that time, or some people still thought it was a comet and it would be coming on a parabolic orbit. So the big triumph here in this table is that it's on a circular orbit, more or less circular orbit, and clearly a planet. The mystery is that it's not quite where it's supposed to be, and he makes some comment somewhere down here where he says, you know, here's my theory, here are the observations, they don't match exactly right. It's because the observers are really not that good, and my theory is perfect. This is the way it still works in astronomy these days. He does suggest right down at the bottom, it's like, well, there's an alternative possibility, and maybe there's something else out there. So in 1820, people started paying very close attention to where Uranus was and measuring its position as accurately as they could. And for the next 25 years, it kept on being measured, kept on being measured, kept on being measured, and it kept on being wrong. It did not fit exactly this theory here. And by about 1840, it was generally accepted that there was probably another planet out there. And the problem was that nobody knew how to take these data and figure out where the planet was. So often when you hear the story, you hear of Leverrier sort of taking data and realizing there was a planet and becoming hugely famous for it. He did become hugely famous for it. He did take the data to figure out where the planet was. But everybody knew there was a planet at the time. His big idea was how to take those data and figure out where the planet was. So he takes this table plus the next 20 years and figures out where, comes up with a theory, figures out where the planet should be. He describes it to the Academy in Paris, and they all sort of politely clap their hands and say, well done, because they were very impressed with his math. But I don't think they actually really were convinced that he actually had predicted a planet, because that's like, you know, using physics to make actual predictions of the solar system just didn't seem quite right. So they didn't really mount a very serious search for it. And finally got frustrated, sent a telegram to Berlin. The director of the observatory was out drinking that night, basically, and didn't go observe, but his assistant did, Gal. Gal went and found Neptune that very first night. So this is the lesson to you: do not be out drinking when you're supposed to be observing. Somebody may take your telescope, do things. So Gal is the first person who saw Neptune. Big triumph. Leverrier became super famous. And within months, astronomers tried to do the same thing again. So for approximately the last 175 years, there have been, we tried to count one time, there have been something like 25 or 30 different claims of a planet, another planet out in the solar system, using some version of the same idea. Invert the observations to find new perturbations and what's out there. The most famous of which, and the most famous, I would say, failure of which is the discovery of Pluto. Discovery of Pluto, the search for Pluto occurred because Percival Lowell had predicted a planet out there based on perturbations of Uranus and Neptune now also, and predicted a general direction, and there was Pluto. And so because Pluto was found in the general direction, and everybody at the time assumed Pluto was the planet for which they were looking, its mass was wrong by a factor, we now know, by a factor of about 250,000. So it in fact was not perturbing Uranus or Neptune, so it was just a happy coincidence that it happened to be there. But it took a long time for that happy coincidence to kind of get erased and for us to realize that Pluto is really just kind of this tiny little dot out there, not a major planet like everything else. So let me quickly go forward in history and set you in place. Here's the inner solar system: Jupiter, Saturn, Uranus, Neptune. There's that crazy Pluto, which seemed weird when it was found on that strange orbit, but now it actually all makes much more sense. If you tilt the solar system on its side, you will see that all of the planets are in one pretty tight plane in the solar system. Pluto is not. Pluto was tilted. Again, that was a clue early on that there was something funny going on with Pluto. And since the time since about 19, is it 19? When was that? 1992. Since 1992, astronomers have been finding many other objects out there in the solar system in this region of Pluto, and they have orbits like Pluto. They have orbits that are tilted. They have orbits that are eccentric. If you look at all of them, it's just a big bird's nest of orbits out there. This is the region of the Kuiper Belt. The rest of my talk, I'll sort of be talking about things that are beyond the Kuiper Belt, so I just wanted to orient you with where we are today. So the story that I'm about to tell, and this one of how we're going to do the 21st time of trying to claim that there's a planet out there by something, except the previous 20 were all wrong and we're actually right, so that's what's cool about this one, is that if you look at the Kuiper Belt, there was this discovery we made back in 2002 of this weird object, Kuiper Belt object still, called Sedna. Sedna is on this orbit that goes way, way out here. It goes so far out that it disappears, apparently, for a little bit of time. Comes back in. It takes 10,000 years to go around the sun. It's a very strange object. The strange part about Sedna, though, is not just its very elongated orbit. It's actually that it never comes very close to any of the planets at all. In fact, at its closest approach to the sun, it is further away from Neptune than Neptune is from the sun. The strange thing about that is to get on an elliptical orbit like this, a highly elliptical orbit, you need to be perturbed by something. Something needs to kick you out of your the circular-ish orbit in which you formed, and there's nothing in the solar system to do that. So that was weird. So we came up with a couple ideas at the time, and I'll walk you very quickly through what the ideas were, which is you can imagine that if you start on a circular orbit, this is now let's have this be Neptune. Neptune's on this orbit right here, and let's have a Kuiper Belt object very close to Neptune. It gets a perturbation from Neptune, comes too close to Neptune, gets a kick. So in very simple terms, it gets a kick right here. It goes on into an elliptical orbit, but it comes back. It has to come back to the same place. It take a single kick right here. We'll just put it onto its new orbit, and that new orbit has to close with the old orbit, so it has to come back to the same place. So it goes like that. It comes back to the same place, but if it comes back to the same place, it's probably going to hit Neptune again, or not hit Neptune. What could hit Neptune? Come close to Neptune, be perturbed again. It gets perturbed again. Maybe it goes onto a more eccentric orbit. It might go onto a less eccentric orbit, but it keeps happening until eventually you get kicked enough times that you get ejected from the solar system. It's basically a random walk, but you're also random walking, and you're getting closer and closer to escape as you get further down. So it's like a random walk on a icy roof that has a cliff on the edge of it. So you'll eventually, if you try walking on an icy roof while you're drunk, you will probably fall off the roof eventually. And that's what happens. These all fall off the roof, unless something happens out here. So let's say out here, you are here and a star comes whizzing by and you get a little bit of a nudge right there, and then you don't have to close back here anymore because you just got a nudge right there, and your new orbit might do that. So our hypothesis, starting back in 2002, was that Sedna was the first of these objects that we'd found that really was the signature of the birth of the sun in a cluster of stars, which is where we think most stars would have formed. But this would have been sort of a fossilized record of these earliest stellar encounters, which was super cool. So we started looking for more of them in 2002 and did not find another one for a very frustrating decade. But starting a couple years ago, several of the objects have now been found, and we noted something really strange about these objects. Here's something really strange about these objects. Sedna is one of these. I can't figure out which one it is. Sedna, I think, is this one. This must be Sedna, the very eccentric one here. And there are 5 others like it. And very strangely, they are, as you can just see visually, they're all sort of pointed off in this one direction. They fan off like this. That could just be a coincidence, but it's weird. If they are fanning off in this direction right now, they won't be in that direction 100 million years from now. They all precess differently. Their orbits move around, point to different places. They're all like hands of a clock, and all the hands of the clock move at different rates. So if they're aligned right now, just due to chance, they won't be very soon. Also interesting is if you, no, this is not doing it. Okay. If the movie actually played, you would see that they're not just pointing off in this direction. If I tilted them on their side, you would see that all the orbits are also tilted in approximately the same direction too. That becomes weirder. So they can, it's at least a coincidence, could be a coincidence that they're all pointed this way. The fact that they're all pointed this way and all tilted to the side is really strange. So we sat down to try to understand why this could be, and the one thing we didn't want to do was to jump up and down and say there's a planet out there, because this is what astronomers do all century long, and they're always wrong. And so we really wanted to show that there was some other way to get this alignment to be stable without a planet. And we tried pretty much everything you could possibly imagine, and nothing worked. And it turns out a planet works really well. You can actually just write down a Hamiltonian. I had to put this in so I could actually have some math in there, but this is the best I could do. You have to read it off the blackboard. Here's a Hamiltonian of a giant eccentric planet in the outer part of the solar system and how it affects these other objects on their orbits in there. And there are a couple things that matter if I can find them on there. So a couple things that matter a lot. You need an eccentricity or nothing happens. And you need something to be pretty massive or nothing happens. And you also need it inclined. Actually, this doesn't include the inclination, but the inclination of the planet has to be about the same too. So it's easy to write down Hamiltonians and think that you have the answer. But the fun thing to do, the more interesting thing to do, is actually try to do a simulation of the whole thing. So we do an n-body simulation where we take an early solar system. We put a planet right here. You can sort of imagine that if you had a planet kind of hugging all of these objects, it might kind of keep them stable. And that's what the Hamiltonian suggested. So I put a planet right here, start the early solar system with Kuiper belt objects, these eccentric Kuiper belt objects going in all different directions, and see what happens. So here it is. I'm going to just play this forward for fun. There's the planet. We're going to stay in the frame of reference of the planet. This is the orbit of the planet. The sun is here in the middle. Each of these little blue things is a Kuiper belt object. And very quickly, a lot of them just get ejected. So there are many fewer even right now. This is going to run for 4 billion years. Get your coffee now. We're looking for things that get stuck right here in this thing. So you can see things precessing. These are the different precession rates of things. These green ones in particular are sufficiently close that they're not really feeling the potential due to this planet, so they just precess and precess and precess. As you get further out, things precess in the opposite direction with respect to Planet 9. And then some start to get captured, like this one, no. This one, no. This one, no. That one, no. How about that one? No, no, no. Okay, so this doesn't work. None of them are getting captured where we thought they were going to get captured. And in fact, if you're paying close attention, they're all over here. when we get to 4 billion years, which is about to happen, you'll see that first off, this has really cleaned out the whole outer part of the solar system. There's very little left compared to what was there. Nothing is really stable. There occasionally things pop up over here on this side, but nothing is very long-term stable over here. The long-term stable objects are all on the opposite side of where we expected. In fact, where the Hamiltonian didn't even consider these objects because we didn't consider crossing orbits in our formulation. So we did not realize that you would actually have these and that these were not very stable. We were pretty surprised at first that this worked out because crossing the orbit of a giant planet is generally considered a really bad thing. But we now realize that now you can see that these things are all tilted the same way. We realize that it's actually, it's a very simple explanation. The way that you get these things to be, they're not stable, they have a longer lifetime. Nothing out there is really very stable if you came back later. The way you get them to have a longer lifetime out there is that the way an orbit works, it spends most of its time out here, and then it comes here and goes quickly through here and comes back quickly through here. These objects do the same thing. They spend most of their time out here and go quickly through here and quickly through here. Imagine things that are aligned in the same way. This spends most of its time out here. They spend most of their time out here. They're spending most of their time close together, and they quickly go unstable. This is basically they're avoiding each other as much as they can. The only objects that live are the ones that best avoid this planet out there. So the theory works. It's an interesting theory to say why we would have these things. Yes. Yes. Sure. Yeah. Yes.
If you're in such long time scales, might one believe that relativistic corrections will have a measurable effect?
So not here, not in the outer part of the solar system. The velocities are just so low that it really makes no difference. If you did Mercury, even if you did Venus over such time scales, I think maybe you have to actually worry about relativity. But at these velocities, nothing interesting is happening. It really is just Newtonian. The numerical simulations are easy. I get my undergrads to do them as projects because they're really straightforward. They're great packages to do, so it works out really well. Okay, so if this is true, what would we expect? Well, we'd expect to find, as we continue to explore the outer part of the solar system, we expect to find more of these objects. And as you saw in the simulations, there's occasionally objects in here, so maybe we'd find some here, but mostly we keep finding these. So what have we found in the last couple of years? There's the original ones. You can see them. They're hard to find. They don't come fast. Let's see. So a year after our prediction, there were these 3 new ones found. 2 of them. The first one that's aligned in the opposite direction, which is okay. Another one there. And this is now a year out of date. There are now 3 more in this direction, and I think 1 more in that direction. It looks pretty good. The worrisome thing, the thing you should worry about, whether there really is a planet that's causing this out here, whether this pattern is really there, is observational bias. When you look up in the sky, whenever I go to a telescope and look up in the sky and look for new objects, where I choose to look in the sky imprints a huge bias on what I'm going to find. And if I only looked, for example, in this direction, where all of these objects come closest to the sun, then I'm going to find a lot of objects like this. If I never look in this direction where these come close to the sun and are therefore brightest, I'm not going to find many at all. And it is really important to take that into account. And it turns out to be very difficult. And I'll show you why in a minute. First, let me show you the current data. If you imagine that each one of these points is one of the now known distant objects, these are the directions that they point. So they point here. They're mostly off in this direction. There's 2 that are pointing down there. Certainly by eye, that looks really quite impressive. There's something going on that should not be going on. The big red dot is the average of these vectors, and the big red dot, if there were no biases whatsoever, then this would be hugely significant, and we'd not have to worry about it. The biases are really important because, well, I'll show you why. So here's where every known Kuiper belt object was discovered in the sky. Here's a map of the sky. They're mostly discovered along this band. This is the band of the ecliptic. This is where all the plane of the planets. They're discovered along this band in the sky. 1, because astronomers look along that band in the sky, and 2, because that's where most of them are. So everybody knows where they are. You want to find them, so you go look in that part of the sky. Sometimes people look up higher because they want to know what's going on out here or up here. And then sometimes there are these super intense surveys, these red things that you can barely see. There are many, many objects that were found in these tiny, tiny areas of the sky. These super intense surveys impart the worst biases. There are many, many objects that happen to be found right here, many, many that happen to be found right here, and here, and here. Interestingly, if you're curious, the direction of those objects that we find is actually right here. It's not one of the more densely populated parts of the sky for observation. So immediately you can guess that it's probably not a huge bias. There are gaps. See this gap right here? Gap right here. Nobody looks here and nobody looks here because that's where the Milky Way galaxy crosses the ecliptic. And looking for objects in the sky with the Milky Way galaxy as a background is hard, and as long as you don't care, you might as well just look over here instead. So that's why these gaps are here. But you can imagine these big biases. The hardest part about these biases, though, is that for the vast majority of the objects on this plot here, the only information that's available is that somebody found that object right there. We now know its orbit. We know how bright it was. We know the day they found it. Very few of these observations come with an actual scientific analysis of the survey that did it. It's a frustrating field because some people just love to go and find a bunch of objects and dump them and say, here we go. And then they go study the interesting ones. And there's no attempt to go back and understand the survey and the limits and everything else. So one of the things that we've spent the last 2 years on is trying to use these data, just of the actual discoveries themselves, to back out what the actual biases are in the entire data set. So here's how it works. What I'm going to do, basically, is ask myself the question, how many of these very distant objects, and where should I find these very distant objects, given these observations, given these discoveries? Now, I don't really know what you had to do to make this discovery, but I do know something about the population of Kuiper Belt objects, and I do know about the latitudinal distribution of objects. So I kind of know if you found something really bright right here, that meant you did a big survey for it. If you found something faint, you probably just did a pointed survey. You can try to use our knowledge of the whole population to back that out, and then it's just geometry. Once you've done that, you just have geometry. So here's some geometry. The first half of this is just geometry. Here's the sun, or us, or something, and let's say we look in this direction and we find an object. And there it is. We find it, we tend to find it close to the sun because that's where it's the brightest. That's our object that we're interested in. That's our distant, eccentric Kuiper Belt objects. And so now we have that object. My question is, where else could we have found it? Where should it, given that we know that this object exists, if there were a uniform population of them, where would we have found it? And the answer you can figure out by saying, OK, here's our uniform population. Let's ask ourselves, there was an object discovered in this direction that was a particular brightness. Which of these families of objects could have been found instead of that object right there that was this particular brightness? So for each of these fake families, we know the brightness at every location along here. Super faint here, super bright here. And so we can just look along here and say, yeah, it would have found all of these because they were close enough to be bright enough. And therefore, there's a region here. This one discovery shows that we were sensitive to objects that were pointing in this direction. Maybe there was an object found over here. The object that was found over here was very bright. And in fact, this object never becomes that bright. So it has no sensitivity to this object out there. And we get no understanding of the biases that are in there. It's a little more complicated than that part of the discussion. But that's really all it is. It's just geometry. It's just taking every observation and trying to back out what we could have found. So for every distant object, we back out the bias on where it could have been found. And you get a plot that looks sort of like this. This is all those objects. Remember, they point like hands of a clock. This is the direction of that clock. Longitude of perihelion is the actual orbital element we're looking at. Between 0 and 360, here's a bunch of the objects. This is the bias as to where it could have been found. So if you were just selecting randomly, this would be a probability distribution function. The blue dots are where they were found. Sometimes this particular object, where's my favorite one? RF98. 2013 RF98 was found, for those who follow these things, by the Dark Energy Survey in South America. And the Dark Energy Survey is in this particular version of the part of the Dark Energy Survey, they were going for super faint objects, looking for supernovae. Well, they were repeating many, many times in the same spot, so they were getting to faint things. So this object is one of the faintest in the data set. And in fact, it could have only been found right there where it was found. So that one is a huge bias. They were pointing there and then pointing there and then pointing there, and they're the only ones who could have possibly found that up. Well, it could have been found over here a little bit, but mostly that's it. So you can take those sorts of biases and basically select a new population randomly from the probability distribution functions, and ask yourselves, what should this average red dot be? And each of these little dots in through here is the average of one of 100,000 random iterations of this number of objects, each with their probability distribution function. And the average of the averages is right there, which is a little bit displaced from 0. The fact that this is not right at 0, the fact that this points this way, shows that overall there's a bias towards finding things pointing off in this direction. And that comes mainly from that one survey that was looking in one spot. Our observations are more extreme than about 4% of the random iterations. 4%, it's not a huge number, or it is a huge number, or it's not a small number or something. But it's OK. So that's the probability that you would find something this extreme due to just random chance and bias is about 4%. So the alignment is about a 4% effect. You can do the same thing now for the tilts of everything. So imagine now that we're looking at this plot is now not the direction that they're pointing, but it's the direction that the orbital pole is pointing. So if an object is tilted like this with respect to the plane of the solar system, its orbital pole is that way, and I would plot it up here. So anything that plots right there is in the plane of the solar system. Anything that plots off of here is tilted from the plane of the solar system. And again, you see that the average tilt is off here. You can do the same thing. It's a lot more complicated but you can imagine where the biases come from. If I look right here, what am I going to find? Well, I'm going to find objects that have orbits that go along the ecliptic. So I can find anything that has a 0 inclination. But I can find inclined objects. They would cross the ecliptic here. But I can only find inclined objects if they cross at this location. So there's a range of pole positions for every single observation. There's only a select set of things I could have had a chance of finding. And then we do this whole thing with the brightness and everything else. And it ends up being these complicated two-dimensional biases. This is for each object has its own bias in the same way. And they're weird looking. So, but each of these little stripes. So again, if you plot right here, that means you're mostly biased towards finding thing in the ecliptic. Most of the observations are in the ecliptic. Any observation in the ecliptic easily finds these things. That's where most of the bias is. Occasionally, there are these high inclination surveys, and then they have these stripes here because they would have found something at the latitude of their survey, but then things at different nodes that were going on this way and this way. And these big stripes are, again, due to couple of the big surveys. All of the background is colored in. You can't see it. It's just from the sort of otherwise random sets of observations. OK, so we do the same thing. And that's the same slide. I don't have the right slide. OK, so imagine that this is not the same slide. I put in the wrong slide. Imagine that I did this again, and I did it with 100,000 iterations. And it looked not like this, but like the real one. But it would look more or less like this. The answer there, it's about 3.5% chance that you would be as extreme. You can't just multiply those two together. They're actually not independent. So you have to do a third full analysis where you do the full biases for all orbital elements. And you get something like that the probability of being extreme in all the axes is about 0.2%. 0.2%, I'm pretty happy with that one. I think that it took us a long time to get to that number because trying to figure out how to do these biases was a big problem. So this was an open question for, I would say, the last year. People were still worried that maybe that these effects are not particularly strong, and it's just a biased set of observations we're looking at. And I think it's pretty clear these days that it's not biased. There really is something going on that causes objects to be clustered in one direction where they're pointing and tilted in one direction. To date, the only thing that really works is an object like this giant planet that's out here that's putting things in this way. One other thing that actually does work too, and interestingly enough, a paper on this just came out on Sunday, but it's kind of an obvious point, is that if you took this planet and our canonical planet was about 10 times the mass of the Earth. If you take this planet and you turn it instead into a ring of material that's 10 Earth masses, and situated and orbiting through here, has exactly the same effect, because most of the effects of this planet are not due to close encounters. They're actually just long-term gravitational, long-range gravitational effects and long-term gravitational effects, and dynamically, it's the same thing. In fact, in that Hamiltonian I showed you, we actually make the approximation that the planet is broken up into this sort of orbit. So you could do it with a ring, but you have to figure out why the ring is there and stable over the course of the solar system. So we'll have it with a planet instead. That kind of makes more sense. OK, so that's the first half of the talk. First half of the talk is, usually that would be the whole talk, because I would mostly be trying to convince you there's a planet out there. But I want to get to the fun parts instead. So you should be at least moderately convinced that there really is a planet, or that there really is something going on out there, and that a distant eccentric planet is currently the only hypothesis that actually works. Some smart astrophysicists may come up with another one someday. They've had 3 years. They've failed. You know, these theorists are really good at explaining things. The fact that no theorist has come up with any other viable alternative is shocking, for one, because, I mean, they're really good at making up things. And I think it's a good indication that this is really, the effect is real, and there's really nothing else out there. So when people ask me, like, well, do you really think there's a planet out there? I would say that the probability that the planet is out there is pretty similar to the probability that clustering is real, or that it's not real. So, you know, I would give a 0.2% chance that there's not a planet out there. OK, but that doesn't help me find it. So I'd like to find it. So how do you find it? Well, what you would like to do is take these orbits that are being affected by this planet and use them to tell you where the planet is. We know some stuff. We know, in general, that if the orbits are over here, the planet's orbit has to be like this. We also know that if the planet is tilted in one direction, that it tilts these objects approximately in the same direction. But the details are hard to work out. So I'm going to show you for the rest of this talk. I'm basically going to walk you through some of our simulations. So we do these, again, like the one simulation I showed was just one early iteration. These days, for every potential Planet 9 that we would like to investigate, we take about 40,000 initial particles, we integrate their orbits for 4 billion years, and we watch what happens. And rather than show you each of those evolving in time, I'm going to show you the end results in ways that I never actually intended to show in public. These were all just for me to kind of understand. So they're kind of ugly, but pay attention to these first ones, because I'm going to show you a lot of them. So if you miss what's going on in the first one, you won't see what's going on. So here's what's going on in one of these ugly things. First off, this is the one to start with. It's an ugly color table too, really. This is the one to start with. Is here are the pointing directions of all of these Kuiper Belt objects over 4 billion years, between 0 and 360 degrees. And this is the distance that they are away from the sun, the semi-major axis. And so what you can see from this one is that out to some distance, it's uniform. There's no structure at all. And suddenly, around some distance, in this case, it's 300 AU. You don't have to be able to read any of these things. At around 300 AU, the structure emerges and things become aligned. At 180 degrees means 180 degrees different from where the planet is, so anti-aligned with the planet. And there's always a couple of objects over here, too. OK, so that's one thing to notice. The other thing to notice is this plot here is again, those pole positions like I was showing you before. So here's average pole positions. For this particular iteration, the average pole is about right here, the average pole of the affected objects in the Kuiper Belt. So I take a cut here and only plot the ones that are outside. Inside here, it's all randomized. And this one is actually a weird plot, but I find it useful just to watch the evolution here, which is if you take all objects beyond the wall, we call this the wall, take all the objects beyond the wall and plot their direction of longitude of perihelion is what this is called, plot that versus how far they are away from the pole, their inclination, you see this. You see this clump again. This clump is the same as this clump. But what's interesting is then to look at all the other objects. So things get peeled off of this clump, and they go into these high inclination loops, come back down again. These objects up here are literally retrograde in the solar system. They're going the wrong direction. There should be some of these objects here. And these objects get pulled off into these aligned clumps too. Okay, so stare at that for a moment. We're going to look at a lot of these, so you're going to have to learn what they look like. So we did a lot of these to start with just to learn some of the effects. So here's this number. All these numbers are orbital elements of the planet that you don't care about. There's a mass. There's the inclination. I'm going to show you what happens as you tilt Planet 9 over time. The main thing that happens, you're going to see this is going to move. So right now, at a 5-degree tilt for Planet 9, your objects affected are only pulled a little bit outside, and you get a very nice alignment in through here. Two things happen. This moves, but this part actually falls apart. And you'll see it fall apart down here, because you'll see that as the planet gets higher and higher inclination, more and more of these objects get peeled off to the side here and become unstable. So there's 10 degrees. This has moved. That's getting a little uglier. You can see why. 15 degrees, ugliness is getting worse. 20 degrees, it's really kind of crazy down here. Things are getting tilted up higher, though. 25 degrees, it's getting higher, but things are getting also more messed up. This confinement is dying. Oh, this plot shows you the fraction of objects that are confined within 180 degrees or within these two lines. And you can see that that starts to go down as the inclination goes up. 30 degrees, it gets really bad. 35, you almost have lost all the structure here because it's quickly pulled away. And by 40, there's nothing else going on. So we've learned something interesting, I think, is that the tilt of Planet 9 better be lower than about 30 degrees. Our original paper, when we hadn't really done any of this, we just made up some order of magnitude numbers. And I think our first canonical numbers were like a mass of 10 Earth masses and 30-degree inclination and 800 AU distance. And those numbers don't work very well now that we've done a lot more simulation. So let me show you what happens, another effect. And one thing also that happens is that as you increase the mass of the planet, the main thing that happens is the width of this clustering decreases. So here's the mass, this very first number. The mass here is 4 Earth masses, semi-major axis of 500, and very broad clustering. I'm going to crank the mass up 4, 5. It's getting narrower. And it actually comes in these two peaks that are right by the edges. Eventually, these two peaks will merge, which will be an important point. 7, these two peaks have mostly merged, and it's gotten much narrower. 10 is nice. 12, look at that. I love 12. Look how nice that is. You get a very nice, tight little cluster in there with 12. It looks pretty nice and pretty. OK. So that's all well and good. Early on, we tried to use those different things, the width of the wall, the width of the clustering, the location where the clustering starts. So I didn't show you that. I should have mentioned that. I don't have a demonstration of it. But the location of this wall, where this wall starts, is a function of, mostly it's a function of the closest approach to the sun of the planet, so the perihelion distance of the planet. So you could basically think of that, though, as this number, the semi-major axis, as that number gets higher, as the planet goes further away, this wall moves outward. If you push this planet closer in, this wall moves inward, too. So the good news is that all of these different effects are going on based on the characteristics of Planet 9, and that tells you that you can somehow use all this information to figure out where Planet 9 is. So we, early on, did some quick parameterizations, like width of the wall, location of, width of the effect here, location of the wall, average position of this, the spread in this here, and you can sort of look around and explore parameter space that way. But it's a pretty crummy way to do it, as everybody would know here. So we are now doing, I think, sort of the right way to do this and to figure out what are real limits on where we should go looking for finding this planet. And we're doing it by a relatively simple likelihood calculation. So rather than parameterizing anything, we simply take our simulations, we take the observations, we ask ourselves, what is the likelihood of finding these things? So here's an example of what we do. This is basically, again, one of these same plots, but now I'm only showing these two things that matter. So this is the distance versus how clustered it is, and this is the pole position. These white dots are the real observations, and we're basically trying to match them, but now we're trying to match them in a likelihood sense. So one thing that we don't do is have any good handle on how to deal with how far away the objects were detected or what their semi-major axis was at the time. So we ignore that parameter. We don't try to fit anything in this direction. Basically, we normalize every distance to 1 here. So the real question is, for this object, what is the probability that it would be detected somewhere along this strip? And you can see it sits in this relatively high probability region, or at least on the edge of one. This object is the one that's not aligned. It sits in a pretty low probability region. These all fit in different spots here. And then we do the same thing with the poles. We actually do all this at the same time. We don't do these separately, but I can't really show you all at the same time. OK, so let's look at some of these. Our first ideas were that Planet 9 was something like 10 Earth masses and at something like 800 AU. So we did those simulations early on. This just turns into a simple likelihood by multiplying all these probabilities together, and you can plot the log likelihood very nicely and see what you get. So 10 Earth masses. Here's a likelihood over here. This is without a label. That's semi-major axis. These were our original ideas. That it was right here. And it's the likelihood is peaking there. So this is we're doing these likelihoods, and each simulation takes about 4 days to run. So mostly in astronomy these days, everybody would if you can calculate likelihoods, you might as well do MCMC. So we do MCMC, but it means something different than what you think. MCMC to us means Mike chooses multiple components. So I do a simulation, and I then decide what to do next. The reason is because in the year and a half we've been doing this, we now have 100 simulations that I'll show you. That would be a pretty lame burn-in for MCMC at that point. So trying to do it by that is not going to work for us. So we do simulations, we examine them, and use our brains as part of trying to figure out what's going on. So when you see something like this, where there's a bunch of objects at one spot, it's because I looked at that and I was curious about inclination, so I ran a bunch of different inclinations to see what they looked like. And in fact, when you run a bunch of different inclinations, you find that you also forgot the label, but in inclination, the likelihood peaks up here at about 15 to 20 degree inclination. Inclination is the tilt of Planet 9. So we originally had thought 30 was the right answer, or we didn't think it was the right answer, but that was our sort of hypothesis. But it really is much smaller. So for that particular version of the planet, it was pretty low. OK, let's look at what that looks like, though. This is this is the simulation for, you can now see it, 800 AU. It's got an eccentricity that you don't care about, 15 degrees, 10 Earth masses. It fits. There's the clustering. The wall, as you can see, is much further out than we realized. There are fewer number of objects on here than you saw in some of those early plots, because I've been very conservative about what I count. So I've taken the things that are the least affected by Neptune, because I don't want Neptune to mess up my story too much. But it doesn't matter. If I'd done more objects, you'd see the same thing. So the wall is actually here. Only 3 objects are, there's one. There's 4 objects in the cluster, and these other ones are all in some part of the wall. The wall is less, inside the wall, there's still some structure, and you can see it pulls it out there. But it's not really what I thought that this was going to look like. I was a little surprised at how kind of crappy these were. So one question we had is what if you try to push the wall in and capture these objects inside the cluster? So you need to push the semi-major axis in, which we did, and we tried 500s and even 450s, and it works less well. But if you crank the mass down, you can actually make it work better. So here's now the same in green, the ones I just showed you, 10 Earth masses. If you do 7 Earth masses, you can actually get a pretty good fit down here at about 500 AU. And you can see I enjoyed 500 AU, so I spent some time at 500 AU. And it looks nicer. There you go. These guys are all in here. You have these horns that come out if you're in that one regime that I was showing you before. These 2 still aren't in it, but that's pretty good. The likelihood is about the same. I want to show you, again, what happens as you go through inclination. Particularly watch this. This is not a very good fit in inclination. They're not all captured in here. But if I That was 5 degrees inclination. 10 degree inclination, this starts to get better while this starts to get worse. So there's a sweet spot right around 15 or 20 where these are getting better. This is starting to get terrible. 25, 30, 35, 40 is just junk. So again, if you look at, oops, that's not inclination. Look at inclination, you get the same thing. So once you've played the game of cranking the mass down to 7, you might as well keep on cranking it down and see what happens. And we were quite surprised that the best fits, we went all the way down to 3 for some. The best fits are actually the 6 Earth masses. That's smaller than I had originally anticipated. But our original paper said somewhere between 5 and 20, so that's, 10 is 6 to astronomers. What's really surprising, though, is that these ones that are 6 Earth masses, if you now do a full set of runs with semi-major axis distance, these are the ones I was looking at before at 800. Here was 500. There's a little better. The best fits really crank up strongly here at about 310 AU. So I'm gonna rant about 310 AU in a minute because this is actually crazy. Inclination again, it's pretty good. It's about there's 15, 10. So it's a moderately low inclination. Here is actually that best fit. It's moderately low inclination. Here's 20. 17 is the inclination. Moderately low eccentricity, 0.2. Quite close. I mean, okay, so 310 is 10 times further than Neptune, but compared to what I was talking about before, that's pretty close. 6 Earth masses is less than I would have guessed. And here's the fit. So it captures these 2 objects into the cluster. The likelihood likes that. It fits this part much better, which is nice. And I'm just going to compare it to the best fit at further away was like that. So here's the difference between these two. You can really see that the pole fit is doing much better, and you're fitting these things better, and even everything is fitting just a little bit better. So, all right, so 310 AU is weird. Why is 310 AU weird? When we first proposed the existence of this planet, we thought it was something with a semi-major axis of maybe 700 and eccentricity of maybe 0.5. That puts it pretty far away, particularly if it's at its most distant position from the sun. It's aphelion, it's 1,000 AU away. Things get fainter in the solar system from reflected light by 1 over r to the 4th. Putting something 1,000 AU makes it really, really faint. So not surprising that we hadn't found it. Making it 3 times closer, or even 2 times closer, gets it a lot brighter. Something that's 310 AU could be quite bright. So here's a question for the astronomers out there. We heard yesterday that the solar system is weird because it doesn't have anything between the mass of the Earth and Neptune, and now I would say it does. 6 Earth masses is just in that spot that there was a lot of discussions of yesterday about planets. So I think I know something about the orbital elements. What I'd really like to know is how bright is this thing? How am I going to find it? How bright is it? So I don't know anything about the brightness of the object. I don't know anything about what it's made out of. I only know its mass. It could be 6 Earth masses of hamburgers. I don't care. All I care about is gravity at this point. But there are astronomers out there who worry about planets. So they have opinions. So let's just collect opinions. Who wants to tell me how big a 6 Earth mass cold planet is? Nobody knows the answer, so you just have to guess a number. So you planet people, give me a number. Give me a number. I don't care what it is. What's a number? Give me a number. 2 1/4. I like that. You're just going to nod in agreement. Come on, you got to come up with your own number. You can't just nod in agreement. That's not fair.
I would say 2.
2. I asked Hilke yesterday. She said 2. So nobody actually knows, but OK, 2. 2 seems pretty reasonable. Harder one is, so now you know how big it is. Then you have to know how reflective it is. It's tough to know. There have been theoretical models of how reflective it should be, and they come up with the answer is 100%, because it would be so cold that it wouldn't have anything in its upper atmosphere because it would all have condensed out, and so it would purely scatter light straight back at 100% efficiency. That's optimistic to me, so I'm willing to believe it's a little bit darker than that, maybe more like Neptune or Uranus. You can come up with your own number. When you do those numbers, now you know how far away it is, even at its most distant, its aphelion position. You know how far away it is, you know how big it is, you know how reflective it is, you now know how bright it is, and it is shockingly at its faintest, something like 20th magnitude. 20th magnitude, all the astronomers should be gasping right now. The non-astronomers, 20th magnitude is, okay, you can't quite see it with your backyard telescope, but there are people with their own backyard telescopes who can get to that depth. You don't need super fancy, big professional telescopes to see something that's 20th magnitude. You know, any college that has a 24-inch telescope on campus and is not in LA can probably see something that's that bright. Not only that, surveys have been done of the entire sky to that depth, and it's not been found. So this worries me. I lose sleep over this. But let me. So sometimes I think something's just wrong, and sometimes I think the universe is conspiring against me. And then every once in a while, I remind myself of just this other fun fact, which is, you know, so I showed you this calculation where I showed you the pole positions and the pointing, and those are two separate calculations, and you put them together. Interestingly enough, if you do them separately, here's the likelihoods using only the direction that Planet 9 is pointing. They ignore the poles entirely. Who cares about the poles? And what do you get? Well, that peaks strongly at 310. It's not as strong compared. It doesn't discriminate against 500 and 800 quite as much, but it's peaking at 310. If you didn't know anything about the poles, you would say Planet 9 is at about 310. That's kind of interesting. What if you didn't know anything about the alignment, but you only had the poles? Now, there's no reason if either it's just weird bias or if there's some other physics going on, there's no reason that that the poles independently would give the same answer. And the poles independently give exactly the same answer. That's weird. That means that both things, if there's some weird conspiracy of either just not enough data showing us something, or of biases, or wrong physics, or anything else, then it's a conspiracy on two separate things conspiring in the same way, showing the same thing. I actually really believe, I think, that Planet 9 is at 310 AU. And I don't know why we haven't found it. So this is why I lose sleep at night. There is one possible reason that we didn't find it. Early on, I showed you that picture of the sky and said, nobody looks in the Milky Way galaxy because there's too many stars there. People always say, when they can't find something, they always say, it must be in the Milky Way galaxy. Might be in the Milky Way galaxy. It turns out, just by dumb luck, that the aphelion position, the most distant point from the sun, and the point where it spends most of its time, is centered directly in the Milky Way galaxy, just by dumb luck. Maybe that's why it hasn't been found. Even in the Milky Way galaxy, it's hard to hide something that's 20th magnitude. So maybe it's a little smaller. Maybe we don't know planet sizes, cold planets very well. Maybe it's darker. Maybe there's knobs you can turn that make me worried. There's one other thing that you should be worried about. Is anybody worried about this plot up here on the right at all? You should be worried about it because it fits kind of, except that the highest likelihood spot in the center is avoided by everything. So that's weird, but because I did one thing that I cheated, I didn't show you this, which is that you really can't just do the models. You have to do the models and multiply them by the biases that I talked about in the beginning. So what you really get when you do that, it's ugly, so I didn't like to show it, but what you really get, and I apologize, it's rotated. This is actually the real rotation in the sky. This is just with the model, but you have to look at those biases. So I'm going to show you the biases. The sum of all the individual biases is not really quite the right thing to show you, but I can do it. This is where the biases get. So there's a reason that all the objects are found where they're found, and it's because the biases conspire to make it not be there in the center where the highest thing is. So if you multiply the biases by the model, you actually get some really ugly looking thing, but that's actually the thing that we're calculating the likelihood. So I'm not going to talk anything about the search for it because we're off searching for it. I don't know where it is. We've searched, this is the main region of the sky that we think we've figured out where it is based on all these likelihood models. And we've kind of done this big chunk of the sky right here. But we've avoided, if you know your sky, this is the Milky Way galaxy right here. We've kind of avoided it because that's an ugly place to look. We're off to the telescope in a week and a half to really go beat hard on the Milky Way galaxy. Okay, you don't care about that. I'm genuinely sort of baffled and nervous and irritated and all of the above, because actually I'm pretty happy with the way this analysis has worked. I think it's the right way to do it. Please tell me that I'm wrong, and tell me how to do it right. And it really tells me that there's a planet in a specific place, and I'm not sure it's possible anymore. I mean, eventually we'll go do the galactic plane, and then I won't find it there, and I'll have to say, oh, well, you know, it's actually, I can't rule out all of the sky. There's a region around Sirius, the brightest spot in the sky, where it must be, because that's where the only place it could still be hiding. At that point, you know, you should just shoot me and put me out of my misery. But it might be coming soon. So I'm genuinely baffled. I hope that maybe we actually find it soon. I'm oddly pessimistic at this point. I wonder if we're doing something wrong, if we're missing something fundamental, and I don't know. So I didn't really mean to end on a down point, but this is my down. I am not worried that it's out there. I'm just worried that we might be doing something wrong about trying to find it. I do want to end on one little last point, which is, of course, this is the fabulous Plan 9 from Outer Space poster made, fixed up. But one of the interesting things about the original Plan 9 from Outer Space poster was this little, and the movie itself, this little scene right there. Nobody's ever looked very closely. Can anybody read right there the gravestone? I mean, it's actually, it's pretty cool right there. It said it right there. 1958, they already knew that it was Pluto was about to go. So that's